Welcome to the Quants Masterclass. Here we're going to be moving into applying probability ideas. We come across conditional probabilities and Bayes' theorem. Now we don't need really to apply Bayes' formula, but it's worth having a look at. Actually what you'll find is it's a lot easier with these conditional probabilities to draw trees and picture what's going on and just pluck your probabilities from the trees rather than applying arcane formulae here. But what we're going to do in particular in this section is we're going to make sure we can deal with a discrete probability distribution. Make sure we know what that is. Make sure we can strip out the mean and the variance of that and the standard deviation accordingly. And we're going to make sure we can deal with conditional probabilities and the trees, like I say, and a brief allusion to Bayes' formula at the end here. Right, so first up, this discrete probability distribution. So what is that? Well, a discrete distribution is one that can only take a finite amount of outcomes. You might sort of think, aren't all distributions like that? And the answer is no. We did touch on this in a previous module, discrete shoe size, where we have a probability of getting a certain shoe size, whereas continuous is more of a measurement, and any individual measurement has got a very low probability of occurring, and there's lots of them. So with a discrete distribution, what we know is that there's a usually small finite amount of states or outcomes or values that we could see. In this particular case, our observation is EPS. In this table here, you can see Bancourt's EPS varies according to these four states that we could be in. So that makes it a discrete distribution because there's a small amount of finite states that we could be in, each with what's called a mass, a probability, a non-zero probability of occurring. So 15% chance of 2.6 and so on. Now to get the mean of this distribution, to get the expected value, it's quite straightforward. We don't need this long formulae here or this ugly formulae. All you're going to do is take the probability and multiply of a particular value, multiply by the value, and you'll get probability weighted values, add them up, and you will get the expected value. So the expected value of a distribution is simply the probability weighted average of the values of the distribution. So hopefully those numbers pop out relatively quickly. We're checking here that your probabilities add up to 100% or 1, as they should do. When you add up these probability weighted values, you get 2.34, which is the mean of the distribution. So that's us carrying out this relatively simple calculation. That, of course, is the first moment of the distribution, the mean. The second moment that we're interested in, of course, is the variance and the standard deviation. Now, remember what variance is. Variance is your average squared deviation from a mean. Okay, so what we're going to do is we're going to look at each value again. So these two columns are exactly the same as the columns on the previous slide. All right, we're going to look at those two values, and what we're going to say is, okay, given that our mean, we just calculated our expected value for the distribution to be 2.34. Given that our mean is 2.34, what is our squared deviation of each value? So yeah, this is from the previous slide as well. That's fine. What we're going to do is we're going to think about how far away each observation is from the mean squared. So for example, in that first observation here, we're going to think about how far away 2.6 is from the mean of 2.34 and square that, all right? And then we're just going to probability, that deals with this term, then we're just going to probability weight this. So we're going to multiply by this column number 1 here, all right? So we're going to multiply this by 0.15, okay? So if we do that, we might as well do that first one on the calculator to make sure it's making sense. If we do that, we're going to go 2.6 minus 2.34, the mean. That's the deviation. All right, so that's obviously 0.26, I should say. Then we square that. All right, so the squaring comes in here. So square that by hitting that key, and then multiply by the probability of seeing that squared deviation, which is 0.15. Okay. So when we do all of that, we get 0.01014. That's how you get that number. All right, you can practice and make sure that you get these other numbers here. For example, this must be 0.45 lots of 2.45 minus 2.34 squared, and so on. All right, when you sum those up, you get to variance very quickly. All right, the sum of those numbers is your probability weighted squared deviation, which is your variance. So then you can take the square root of that to get back to your standard deviation. And your standard deviation is in the original units, so we're looking at dollars here. Now there's a box there that says this is much quicker on the calculator. Once again, you know I'm not a fan of relying on the calculator. I've said that before in a previous model. But maybe we do get a little bit of a speed up here when we think about what we're looking at. The way to do it actually when you've got a discrete distribution like this, first of all, go to your data sheet. So second 7. All right, it's got some junk in there from before, so I'm going to clear it. So second CEC clears whatever data sheet you're in. And what I'm going to do is I'm going to make my x variables equal to the x variables. So x1 is going to be 2.6. Okay, that's fine. Enter. Whenever enter's on the screen, don't forget you have to enter. I'm going to arrow down now. Here's the trick. I'm going to use, for y01, I'm going to make that the whole number percentage probability. So instead of 0.15, I'm going to make it 15. Okay, so y01 is going to be 15. It's just a feature of the calculator that if you make your y values whole number percentages, which represent probabilities, and they add up to 100, then the calculator knows you're looking at a discrete distribution. Okay, so I'm going to arrow down. x02 is going to be 2.45, and the probability, so enter, probability y02 of observing that is 45 in whole number terms. Enter. Make sure you enter them as whole number percentages. And then arrow down. x03 is 2.2. All right. And arrow down. The probability of observing that is 24 in whole percentage terms. Then the final data point is 2. Bang on. And we arrow down. y04 is 16% in whole percentage terms. Okay, great. Now, that was in the data worksheet, wasn't it? Second 7. I'm going to go to the stats worksheet to analyze that data. And I do want to be in mode 1-V. Remember, there's lots of modes here. You can toggle through them by going second enter. There's lin, there's ln, there's exp, there's power. We're interested in 1-V, which eventually comes back round. Once you're in there, you can arrow down and you see that there's 100 data points. Well, your probabilities add up to 100%. Then the mean is 2.4035. We knew that. But here's the shortcut. Not that one. We're not interested in that one. That's a sample standard deviation, which actually is irrelevant here because we're looking at a whole distribution. It's that one that we're interested in. 0.1969. There you go. There's the population standard deviation. Why is this a population standard deviation? It's a population standard deviation because we've looked at the whole distribution here, the whole 100% of outcomes. Okay, so much quicker on the BA2+. Really much quicker. I don't know. Don't be lazy. Understand what you're doing. And don't rely on the calculator too much. Okay. All right, moving on. So let's talk a little bit now about conditional probabilities. So we should know that probabilities, of course, are a number between 0 and 1. Probability of 1 means it's definitely going to happen. Probability of 0 means it's not going to happen. When it comes to dependent and independent events, they're pretty straightforward definitions. Right? If you've got two events, A and B, all right, so something random like a dice roll or picking a card from a pack, or something coming out of a distribution, like a return coming out of a distribution. If the two events are independent, then the occurrence of one event does not affect the probability of another event occurring. Okay, that makes them independent. In stats, what we tend to do is we tend to write PA line B to represent the probability of A happening given we know B has happened, right? If events are independent, we know that the probability of A happening given we know B has happened is just the probability of A happening because A is independent of B. So the example that we give here is a fair coin. As consecutive flipping of a fair coin, the probability of a head in any individual flip is 0.5, regardless of what the coin has said before. So the coin is independent of its previous flips. Just because you've seen 10 heads in a row, it doesn't change the fact that the probability of a head happening in the next toss is still a half. It's the probability of 11 heads in a row that's really unlikely, right? Now, it's a fallacy that, that's a mistake that a lot of people make in the casino when they look at the roulette wheel and they say, look, there's been 10 reds, so there's bound to be a black coming up soon. It's false. The spin of a roulette wheel is independent, just like the flipping of a coin is independent to what it previously said. So you'll see here that we flip the coin the first time and we get a probability of a head of being a half. That's the same in the second coin toss. The same in the third coin toss. And so to get the probability of 3 heads in a row, that's the probability of seeing heads. And then that's happened, and then there's half a chance you see another heads, so multiplied by half. And then that's happened, there's half a chance you see another heads. It's 0.5 cubed, that's 1 in 8, isn't it? There's only a 1 in 8 chance that you'd see 3 heads if you flipped a fair coin 3 times. The point that's being made here, though, is that the probability of heads occurring does not depend on whether heads occurred in a previous coin toss. So dependent events, well, you know, the logical extension of this discussion is that dependent events, these are events where the probability of an event occurring is affected by whether or not another event has occurred. So the probability of A occurring is, given that we know B is occurring, is not the same as just the probability of A occurring what's called unconditionally, more generally. Okay. So the example that's given here is picking cards out from a pack. We know there's 52 cards in a pack. All right. The probability of getting 2 consecutive aces, well, there's 4 out of 52 chance of picking the first. You know, there's 4 aces in the pack. All right, and there's 52 cards in the pack when we pick the first card. All right, so the probability of getting an ace with that first card selection is 4 out of 52. Now, the probability of getting an ace with your second selection is really dependent on whether you got an ace with your first selection. All right, so the probability of getting 2 aces together is actually, you must have got an ace with the first pick, so there's only 3 aces left in the pack, all right, and there's only 51 cards left in the pack, all right. That really depends on whether you got an ace with the first pick, doesn't it? So that's a conditional probability. The probability of picking an ace from a pack of cards with that subsequent pick, it's changed. It's 3 out of 51 instead of 4 out of 52. So clearly, the probability of getting an ace with your second card is dependent on whether you get an ace with your first card or not. If you hadn't got an ace with your first card, then the probability of getting an ace would be 4 out of 51, wouldn't it? So that's an example of a conditional probability. You know, probabilities being conditional on other events and events being dependent. You know, we do this all the time. It might seem a bit arcane and a bit mathematical, but actually we do this every day, all the time. This is how we interpret the world. We look at things, we assess information, and we update probabilities based on that information. You know, if you switch the television on and you saw that your favourite sports team was, you know, take football, soccer for example, your soccer team was 3-0 up at half time, you update your probabilities. You say, well, the chances of us winning this game are a lot higher. You know, we might win half our games. That's an unconditional probability. But given we're 3-0 up at half time, the probability of winning this game, given we're 3-0 up at half time, this new information is actually 80%, 90%, right? You've changed the probability of winning conditional on the fact that you're 3-0 up at half time. Not all games you're 3-0 up at half time. You're kind of saying just in the specific case when we're 3-0 up at half time, the probability of winning is a lot higher. And it's affected by that new information. We do it all the time, right? You know, I look outside, I see it's sunny. If I go to the park, probability there's lots of people in the park is higher than if it was raining. The probability that there's lots of people in the park when it's raining is a lot lower. So the probability of being lots of people in the park, it's conditional on the weather, isn't it? We do it all the time. But when we do have conditional probabilities, the best way to deal with them is to draw trees and to think about whether the sun's out or whether it's raining. And then you can adjust your probabilities accordingly. Of course, in finance, we don't tend to talk about the sun being out or it raining. What we tend to talk about is other sorts of environments, like whether interest rates are going up or not. Okay, so here's an example of some conditional probabilities with a financial application. We'll just jump straight into it here. We're told the probability of an interest rate increase is 70%. All right, that means the probability of an interest rate increase not happening, we call that the complement. That is 30%, okay, or 0.3. The probability of a recession, given that rates have gone up, that would be written as PR, and then this vertical line I, that's 60%. Now that's telling me the probability of no recession, given that rates go up, given an increase, that is 0.4, okay, 40%. Notice how I took complements on the first observation here. We're saying we're in a world where rates have gone up, then there's a 60% chance of recession. Therefore, if we're in a world when rates go up, there's only a 40% chance we do not have a recession complement, if you like. We're told about what happens if interest rates don't go up. That's what I complement means. Interest rates have not gone up. Probability of recession is 20%. Therefore, the probability of no recession in this world, IC, must be the complement. Notice we always take complements on the first thing, right? See how if you know PR given I, then you take complements PR complement given I. You're still assuming this thing has happened to take the complement, right? And you're still assuming this thing has happened to take the complement here. So you're asked here, what's the unconditional probability of a recession? Regardless of what interest rates do, what's the probability of a recession? Well, a recession can occur when rates go up, and a recession can occur when rates do not go up, okay? The probability that we have a recession if rates go up is just taking the probability that rates go up and then multiplying through by the probability of recession given that rates go up, okay? This is how you combine probabilities when they're conditional upon each other. You're just multiplying through because we've got this world here that's happened where rates have gone up, and then out of that world we've got the recession portion, if you like. We're multiplying through. So it's what's called a joint probability. They've both happened. Yeah, recession and rates go up. This one here is rates do not go up, and then in that world, given that world, there's a recession. That's really just the joint probability again. So you can put the numbers in here. I've written them all out. The probability that rates go up given that, probabilities that there's a recession given that rates have gone up, that's 0.6. We've said that. Times the probability of rates going up, that's 70% or 0.7. We've said that. Okay. And then we are given the probability of a recession given that rates have not gone up. We said that's 0.2. All right. And the probability of rates not going up, I took that complement here. I wrote that out. That's 0.3. So you can add those together and get 48%. Now, you would be forgiven for thinking this is a bit yucky. All right. You'd be totally forgiven. Myself, personally, I'm struggling not to draw this out. Draw this out as a tree, because then you can see everything and you can pick your fruit as you like, right? So what do I mean by drawing it out as a tree? Well, take the thing you're conditioning upon. In this case, we know we're conditioning upon interest rates either increasing or not increasing, because you can see the probabilities given there as is what you're conditioning upon. This is the probability of recession given an increase. So take the increase and no increase in rates and just draw a binomial fork, all right? Rates are either going to go up or they're not going to go up. And we know the probabilities that interest rates go up is 0.7, and therefore the complement of that we deduced already is 0.3. Now you've got two worlds that you're conditioning upon, and you know that the recession probabilities depend on which fork you've gone down, okay? You're told that a recession given, this here is recession, given that rates have gone up is 0.6. You were told that. Where? Oh, you were told that back here, right? There it is, okay? And then the complements become easy, because you always take complements vertically at a fork, right? If a recession given rates have gone up is 0.6, then a recession complement, so in other words, no recession given rates have gone up, you take the complement on the first one, that must be 0.4. Given rates have gone up, which they have here, only these two things can happen. They must add up to 100%, these conditional probabilities, okay? Vertically, these things add up to 100%, just like they do. All right, do the same on the bottom fork. No interest rate increase, all right? We were told that a recession given no interest rate increase was 0.2. Where were we told that? Told it here, all right? And then take complements vertically on that fork. Therefore, no recession given no interest rate increase is 0.8. Okay, so I don't want to make this too messy. I'm just going to get rid of some of my sketches here. I'm just making the point you take complements on these forks. They always add up to either one. When you get to a fork, one of these two things happens. So they always add up to 100%. So then you can get your joint probabilities, your AND probabilities, by just multiplying along the paths of the tree. So to go along this up and up, if you like, you've got 0.7 multiplied by 0.6, right? That's what that is, 0.7 times 0.6. That is the probability of rates going up and there being a recession. To go along this path and get here, you go up the 0.7 path and then down the 0.4 path. Multiply them together and you'll get 0.28. All right. Similarly, go down the 0.3 path and then up the 0.2 path. Multiply those two together, you get 0.3. All right. You get 0.3 multiplied by 0.2. That's 0.06. And this one here, you got it. 0.3 times 0.8 is 0.24. Now these are the AND probabilities, and they should always add up to 100% or 1, right? Because one of these combinations of interest rates going up and recession has got to happen. But now you are endowed with the ability to answer any question, right? You were asked in this question, what's the unconditional probability of a recession? Well, you're completely on top of the ball now. You've got full vista. You can say, well, look, a recession happens here and a recession happens here. So add those two probabilities up. What proportion of this universe is that? It is 0.48, right? So underneath my scribblings there, got a bit messy, but underneath my scribblings, add those two up, you get 0.48, which is, by the way, what we get using the equation from before. So let's have a look at a CFA example. Same ideas, but a little bit more convoluted in its presentation, and also working out expected values as well. So you've got Bancorp's earnings per share part 2. It's a different scenario here. Probability of declining interest rate environment, 0.6. And therefore the probability of, so that would be interest rates going down. In probability of stable interest rate environment, which seems to be the complement of rates going down, it's a stable interest rate environment, is 0.4. In a declining environment, there's a 25% probability a company's EPS will be 260, 75. Okay, this is screaming out for a tree, isn't it? Screaming out for a tree because we're being given conditional probabilities, right? This is conditional upon a declining interest rate environment. These probabilities are conditional on interest rates declining. So this is screaming out for a tree, all right? In a stable interest rate environment, there is 60%. These are conditional probabilities as well when interest rates are stable. Screaming out for a tree. So we need to calculate the expected EPS and conditional EPS and even conditional variance, as we'll see. We're going to do that. We can only really do that once we've seen a tree. So same message as before. Take the thing that we're conditioning upon, which is the interest rate environment again, and set your tree up by putting a fork in the road for that event. All right. So this is the thing we're conditioning upon. Declining interest rates and stable interest rates. They say unconditional probabilities here, but it's better to think about it as the thing we're conditioning upon. We're told that in a declining interest rate environment, 25% chance the EPS is 260, 75% chance the EPS is 245. So we can draw that on the tree like this. 25% chance EPS is 260, 75% chance EPS is 245. I've actually got values here, which is quite interesting. And then there's a 0.4 chance that the interest rates are stable. And in that world, stable interest rates, there's a 60% chance EPS is 220, 40% chance EPS is $2. So that's what's coming through here. 60% chance 220 and a 40% chance of 2. So you get your joint probabilities, the probabilities of both these things occurring by multiplying through by the probabilities in the tree. 0.6 times 0.25 is 0.15, etc. All right, 0.6 times 0.75 is 0.45. Little trick for you, these joint probabilities, they actually should always add up to that original fork because you're really just splitting that original fork out, aren't you? So 0.45 plus 0.15 is 0.6, all right, and 0.24 plus 0.16 is really just splitting out that original 0.4 there. Okay, so now you can get your expected EPS because you can just weight the EPS by the probability of it occurring, right? Check that you've done this right. That should be 100%. Of course, 60 plus 40 is 100%. So you've done it right. That adds up to 1. And your expected EPS multiplying through gives you probability weighted EPS. All right, you can add them up. 0.39 plus 1 spot 1025 plus. So add those up and you'll get to the probability weighted EPS, which is your expected value, 2 spot 34. All right, on now to the second question. That was actually answering the first question, but I wanted to get the tree set up as soon as possible. So we ended up answering the first question here, the expected EPS of the company, just by kind of like a knee-jerk reaction to building the tree. Let's think about the conditional expected EPS, given that we know that interest rates have declined. Well, given that we know interest rates have declined, we know that we stand here, right? Interest rates have declined. That's this world. We're making this our world now. And so it's all about this 0.25 and that 0.75, those earnings, right? As you'll see, as we go through the answer to this question here, that's answering question 1. Question 2, as we can see, the conditional expectations of EPS, given the interest rates have declined, we're going to stand here, as we've said, and we're going to say it's going to be 0.25 lots of 260 and 0.75 lots of 245. That's our expectations now, given we're standing here. Interest rates have declined, right? So that's where these numbers come in. 0.25 lots of 260, 0.75 lots of 245, given this number here. See how important it is to have the tree as a frame of reference. For what it's worth, that answers question 2, by the way, but for what it's worth, you can think about what the expected EPS is given stable interest rates, all right, which is this 0.6 lots of 220 and that 0.4 lots of $2 if we stand there. All right, so that's where those numbers are coming in. And as you might expect, we've got higher, as you might expect, if you excuse the pun, you've got higher expected earnings when rates decline. And by the way, probability of rates declining is 60%. So if we multiply this expected earnings by the probability of rates declining, all right, and we add the probability of rates not declining or staying stable by the earnings expected when rates are stable, we get the number we first thought of. We get 2.34, which we got via the joint probabilities, anyway. So we're really just double checking there that our numbers do indeed add up. So that's answered the second question, all right? Conditional expected EPS given the declining interest rate environment. The third question is probably the least trivial one, the most complex one, the conditional variance of EPS in a declining interest rate environment. Once again, the tree is crucial. We're in a declining interest rate environment, so we are standing here, all right? And we're thinking about the variance when we stand here. So what you're going to do is you're going to start thinking, and this is where the knowledge of what you're doing really becomes important. I know this constant allusion to the calculator. The calculator is not going to tell you what to do, right? So when you're standing here and you start thinking about how to apply variance here, if you know what variance is, then there's nothing really to think about, right? Variance is probability weighted squared deviation, right? It's your expected squared deviation. We know that your conditional expected EPS here, when interest rates decline, we've just calculated that. That's this one, 2.4875, right? If you know what variance is, so once we're standing at this node here, the expected EPS, given that interest rates have declined, that's that 2.48 figure that we just looked at. Apologies for all the animation here. 2.4875. All right. If you know what variance is, then you know you're going to take this 260, see how far it is away from 2.4875 and square it, and then multiply by this probability, right? That's probability weighted squared deviation from now my conditional expectation. Okay, so that's what's going to happen in the next slide here. When we think about declining rates and we're thinking about variances expected, given that we know rates declined, we know we could have earnings of 260 and 245 with those probabilities. They were in the tree, right? We can probability weight those observations and add them up, and we get the expected earnings given that rates have declined. All right. Then we start thinking about how far away this 260 is from that new conditional expected EPS in this world. All right. So this number here must be 260 minus 2.4875 squared. All right. We'll just check that we can do that, or we'll just check that that's tying up with what we're saying. So 2, let's get rid of all that. Get out of that, please. So 2.6 minus 2.4875 equals squared 0.01. There you go. Just showing how you get it. Then you multiply through by the probability. So that's your squared deviation from the conditional expectation. And then you multiply through by the probability, which is here, 0.25. So multiply by 0.25 and you'll get this number here. Very small number, right? Do the same when we're thinking about the other EPS we could have with a 0.75 chance when interest rates decline. Okay, probability weighting, just multiplying those two things together gives us this, which goes into the conditional EPS, expected EPS. But once again, the squared deviation, this must be 245 minus 260 squared. All right, and this here must be multiplying that by the probability of 0.75. It looks about right, doesn't it? Add those two up and you've got your conditional variance in the world where interest rates are declining. Okay, so see how that relies on knowing what variance is. It's the same concept of variance where it's your probability weighted squared deviation from what's expected. You're just thinking about what could happen now relative to your conditional expectation. It's the same calculation under stable interest rates. Okay, so when we had stable interest rates, the conditional expectation, so the expected EPS, given that interest rates were not going to decline, okay, was 2.12. We did calculate that before. And so this figure here, this must be, just be careful, this must be how far 220 is away from 2.12 squared. So that's 0.08, and when you square h, you get 64, so that looks right. And then you multiply through by the probability of 0.6, right, to get this number. This here must, of course, be how far 2 is away from 2.12, this conditional mean squared. Of course, 0.12 squared is 12 squares of 144, so that's why you get this 144. Multiply through by the probability of 0.4, you'll get this number, add them up, and you'll get the conditional variance in that world. Now notice how crucial the tree is to seeing all this stuff. The tree is really important. Once again, we're going to use trees to attack a CFA Institute, another CFA Institute problem, which refers to Bayes' formula. We'll talk about Bayes' formula in a moment. The truth is, practically, you don't really need it to deal with conditional probabilities. But what is it, I suppose, is what we should discuss at the outset. Bayes' formula is a way of turning around your conditional expectation, your conditional probabilities, I should say, right? So you can derive the probability of B given A if you know the probability of A given B and other probabilities, all right? Other probabilities. It's a way of turning that conditioning around. That's what Bayes' formula does, really. You don't need to use the formula. We'll look at the formula in a moment, but let's use a tree instead because that's a lot more intuitive and a lot more easy, right? So look at this probability tree here. We're conditioning upon whether we've picked a tech firm or whether we've picked a non-tech firm. So there's, if you like, the thing you're conditioning upon. And what we're saying is if you've got a tech firm, the chances that you get a return above 10% is 0.6. Chances if you get a return equal or less than 10% is 0.4. And that's not the case if you've got a non-tech firm. It's a bit tech biased here, isn't it? You're not very likely, only a quarter chance, like 0.25 chance of getting a high return. If you've got a non-tech firm, you're much more likely with a non-tech firm to get a return less than or equal to 10%. Okay, so there's your tree. Now here comes a question which looks quite complex, but if you know all your probabilities, then it's actually really straightforward. So let's complete the tree, shall we? The probability that you pick a tech firm and it returns greater than 10% is 0.2 times 0.6, which is 0.12. Okay, just multiply through by these probabilities and you get these numbers here. Bit of a sanity check. You always check that up to 1, right, which they will do. Bit more of a fine check. Always check these numbers here add up to that 0.2 because you're just carving it up. And those numbers there add up to that 0.8 because you're just carving that up. And of course, they do. Let's make this a bit less messy, shall we? All right, so now you've got your ands, right? These are your ands. And what you can see, these joint probabilities, right? What you can see is that 32% of all firms had earnings greater than 10%. All right? This could, of course, be return. That should, of course, be returns. When I say earnings here, they mean returns. Okay. So in terms of how we got that, we just said, look, if we're looking for returns being greater than 10%, which is what we're looking for here, all right, we can say that there's these ones here, like they're tech firms, but only 12% of the world it makes up these firms. There's also these firms here. There's 20% of the world that makes up these firms, right? Because there's so many non-tech firms. Yes, it's less likely they'll have a high return, but there's only 20. There's 80% of firms are non-tech, so it makes up 20% of the universe. So it's these two, 0.12 and 0.2. That's the world where returns are greater than 10%. So what's the probability that a randomly selected firm has returns greater than 10%? To answer that, that's 32%. To answer the full question here, we're being asked, what's the probability that a randomly selected firm out of this 32% is also a tech stock? Now you can answer this, which is quite a nasty question, quite a profound question. We need to think, okay, can I see this? Can I see how many of these yellow stocks are actually tech stocks? And the answer is, yes, you can. It's this 12% here, isn't it? They are tech stocks, all right? They're not. So, given that you're looking at something from the yellow bucket here, something from that world, which is 32% of the original universe, you know that only 12 out of that 32% is tech stocks, right? So, given you're looking at a stock that's got returns greater than 10%, which is the yellow part of the universe, we know the probability of that firm being a tech stock is 12 out of that 32%. All right? It's the 12 bit out of that full yellow 32% bit. Okay? So you can see here what we've done is we've turned the conditioning around. All right? This question started off saying, hey, given that you've got a tech firm, we can talk about the probabilities of returns. And we've turned it round. We've actually answered a question where, given we know we're in the yellow bit, we know about returns, we can start thinking about the probability that we're looking at a tech stock. That's what Bayes' theorem does. It turns the conditioning around. Now you'll hear and maybe read a lot about Bayes' formula. In fact, the section's called Bayes' formula, but you don't need it to answer that question, do you? You just draw the tree and then you think very carefully about turning the conditioning around by picking out the green stuff out of the yellow stuff. All right. You should practice that. You watch this video again if you need to and practice doing that. Now we know we don't need the Bayes formula to get the answer out, but almost out of curiosity, let's have a look at it. Here it is. In fact, the Bayes formula is this bit here. The probability of A given B can be derived from probability of B given A in this way. The idea is the probability of A, given we know B's definitely occurred, can simply be thought of as how much of this new world, right? This new world, given we know that B's happened, right? That's our new world. How much of this new world does A occur as well? All right, you know, the probability of A and B is on the top here. How big is that relative to our new world where we know B has happened? Okay. Now you can express the probability of A and B happening. This is a joint probability here. You can express that as probability of B given A times the probability that A actually happens. And that's where you flip the conditioning around, isn't it? And so there's Bayes' formula in the big red square brackets there. Now I wouldn't worry so much about Bayes, just a bit of terminology. I wouldn't worry about the formula. You know, the unconditional probability of A, what we think without any information about B is called the prior probability. Once we know B's happened, we update those probabilities with what's called a posterior probability. All right, the probability of A given B. And of course, if A is conditional or dependent upon B, then the probability will change. Now we know using trees that the answer to our question here, which by the way given returns, what we're really looking for here is the probability that we're looking at a text stock given returns are greater than 10%. That's what we've calculated. We know we can actually flip this round using Bayes' formula. We could say that this must be equal to the probability that returns are greater than 10% given we've got a text stock, multiplied by the probability of a text stock. All right, that's the joint probability. That's this 12 here. All right, isn't it? It'll be 0.6 times 0.2. And then we divide by the thing we're conditioning upon in this world. So if we know that this has happened, returns are greater than 10%, we're going to divide by the probability that returns are greater than 10%, which of course is the yellow stuff. It's the 0.32. Okay. So that's using Bayes' formula, and I think it's less intuitive and less visible than just picking the probabilities out of the tree. And so that's why my wholehearted recommendation is that you use the trees here. Okay. Well, look, that completes this relatively small module. Make sure you're good on discrete distributions. Make sure you're good on conditional probabilities. Stay away from Bayes' formula. Stay with the trees. Use the trees to deal with your conditional probabilities and your Bayes applications.